right, everyone, welcome to the EE 2950 SI session, number 2. Today we're going to look at a few more concepts, and we're going to get into some more problems relating to these concepts. So starting off, let's go ahead and look at our Ohm's law. So Ohm's law is going to be our favorite equation in this class. It's just going to be V is equal to I R. And that's just going to relate the voltage, current, and resistance of an element in a circuit. Looking at KCL, KCL is one of our analysis techniques that we have. So if I am going to use a KCL, it has to be at a node, or a node is just a point where these two wires are going to meet. And what this is, we'll have currents entering and exiting. So I can call this like I1, I2, and I3. And what this says is if we sum the ones that are entering and we sum the ones that are exiting, they should be equal to each other. It's conservation of a current flow. So what this means is if we sum all of the currents, they should equal 0. So if we were to write this out, say in option 1, so the first way we can write this is we can say plus I1 minus I2 and minus I3 is equal to 0. So that's saying here if positive is entering and negative is exiting. Now, I've had people ask in the past, can you do it the opposite way? Can you do negative as entering and positive as exiting? And the answer to that is absolutely. Of course you can. All that is moving the currents to the other side of the equal sign. So both methods work, both conventions work, just whatever you're comfortable working with, and just keep it consistent. Okay, let's look at KVL. So KVL is going to be if we have loops. And that says that if we were to sum the voltages in a loop, they should all sum to equal 0. Meaning that if we had something like this, V of S, add our terminals here, call that one V1, V2, and then V3. If we took, and since this is a loop, the same current is going to run through it. So we'll just call that our current I. And what we're going to do is we're going to start on a point, and we're just going to walk around the loop until we end up back where we start. And what that'll look like for us is everywhere we hit a terminal with the current, that's what we'll assign to that voltage. So if we start at the battery, if we start, say, at that point right there, we'll come up, we'll hit the negative terminal of the battery, we'll hit the positive terminal of V1, the positive terminal of V2, and we'll hit the positive terminal of V3, and we'll end up back where we started, so we can set that equal to 0. And so what this really means is that all the battery voltage is given to all of these other voltages throughout the circuit. And say if we don't know these voltages, we can just say, using Ohm's law, V is equal to IR. and we should know the resistance and we know the current. So you can just say I R1 plus I R2 plus I R3. Okay, and that's a typical method that you're going to use when solving some of these circuits, is replacing it with Ohm's law, as we see right there. Okay, let's take a look at resistor combinations. So our resistor combinations are useful because we can take a complex circuit and break it down into a much easier circuit. And a common one we have is series. Now series, they have to be on the same wire. Okay, so if we have something like this, R1, R2, and R3, this is a series combination. If we have something like this, R1, R2, and R3, this is also a series combination. They're all on the same wire. If we have something like this, this is not, because not all of our resistors are on the same wire. That one is not on the same wire, so we cannot consider all of these to be in series. So knowing that, you can actually change it to make it all series. But let's just look at the equation for right now. So our series equation is going to be the sum of the resistors on the wire, which is just equal to R1 plus R2 plus R3 plus dot 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 dot, however many you have. Okay. The second kind that we have is called parallel. So parallel is going to be where we have two wires that are across from each other. So here, they're across from each other. They're on a different wire. I'll write that up here. Different wire. Okay. Looking at another combination. So looking at what we had before, this situation is parallel, because looking at our, there we go, looking at our resistors on the wires, they're on two separate wires. We have this one here, and then we have this one there. Okay, so now the R equation for that one is going to be a little more difficult. It's 1 over R parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus dot 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 1 over Rn, where n is just some number of resistors. So you can actually rearrange this to say R parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus dot 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 1 over Rn. Now, there is a trick. and I'll put this in red, if there's only two in parallel with each other, like this, it is going to be, this will be R1, this will be R2. R parallel is going to be R1 times R2 over R1 plus R2. Okay. This will make your calculations much faster doing it this way. But be careful that you don't misuse it in the wrong places. All right. Let's take a look at current division. So what does current division look like? So if we want to use current division, this needs to be in parallel. And what does that look like? So if we had a circuit that had 3 branches on it, so R1, R2, and R3, and we had a current, which we're going to call I of S, source current. It's going to hit this point and branch off this way. It'll send some down this way. It'll branch off, and this will also come down here. So these currents that we see here are all parts of this bigger current. So, hey, we're gonna go on mute until the end of the questions, okay? So back to this. So each one of the currents that go down the branches, we'll call I1, I2, and I3. So if we want to find a particular current down one branch, so say if we wanted to find the current I1, we could just say I1 is equal to R equivalent over R1 multiplied by I of S. And what is R equivalent equal to? Well, that's going to be equal to the parallel combination. So because all of these are in parallel with each other, we can do that, okay? That's what we're going to have to use that representation. Like we said before, it needs to be in parallel in order for current division to happen. All right, we'll take a look at voltage division. So now voltage division, everything needs to be in series. And if we draw this out, we'll call this V of S. We'll add our terminals plus and minus all the way around. This is V1, this is V2, this is V3, this is R1, R2, and R3. All right. So say we want to know the voltage across one of these specific resistors. So say we wanted to find voltage across resistor 1. Well, what we'll do is we'll say R of 1 over R equivalent times V of S. And here, R equivalent is going to be equal to R of S. And like we said before, all resistors are in series. Therefore, we can use the voltage division. So this equation turns into R of 1 over R series times V of S. All right. And something to note here, some people ask, I get confused on which value goes on top and which one goes on bottom. Well, here, I'll write it out for you real quick. So if I was to do this, and write these two equations. Okay. So in these equations, the smaller number goes on top. Okay, so that means here for this one, R equivalent is less than R1, and over here, R of S is, or I call it R of S, you can call it R equivalent. R equivalent is greater than R1. Big old red box around that. Okay. That is it for the concepts. Does anyone have any questions about the concept section so far? Let's see, looks like we have something in the chat. Nope. All right. That sounds good. Well, we'll go ahead and move on to the questions. Okay, there's one more concept. Apologies. So voltage along wires, they are the same until reaching an element. Okay. So that means that here, I'll do it like this. So we'll start with some voltage value here, and the voltage value here will be the same, voltage value there will be the same, there. It's going to hit this element, it'll travel through, hit this point, and now it will have a new voltage. And that voltage is going to stay the same until it hits this other element. Now it'll have a different voltage. And then it'll come through and it'll travel through this element, and it will change again until it travels through this element. So you can kind of look at these here and you see the groupings. So this voltage is the same, so is this one, so is this cluster, same as that one. So until we actually touch an element in the system, it's consistent. All right, that is the end of the concepts. And now we will go on to some warm-up questions.